Hello everyone, this is Wilson. Let's compute this limit here. So first, when we compute a limit, we want to just directly plug in the number in there and see the form, and we want to check whether that will give us an indeterminate form, or we can actually tell what that function is approaching to, as x is approaching 1 from the right side. Okay, so first thing, we are going to just plug we can just look at the form here. So the form is going to be, let's do some scratch work. And so we have the base, which is x, so we leave it as a blank. And then we are going to write down the exponent. The exponent would be 1 over, and then the x is turned into a blank because we are going to directly substitute that 1 in there and try to analyze the form. So now if we plug in the 1 in there, so 1 from the right, Okay, so let's do the calculation here. So we know that for the base is still just going to be 1 from the right side, right? So we are approaching 1 from the right side for the base. And then for the exponent, we are going to get 1 over. And then now, because we have um, something that's approaching 1 from the right side and then subtracting the 1. So this denominator will be approaching 0 from the right side, because that will be giving us a positive number. And now you can see that when you look at this 1 divided by a small number, then you are going to get infinity. So we are going to get that that's 1. Actually, I don't need the parentheses, so we just have 1 to the infinity. Now, just one thing that's important to remember is that this 1 is not an actual one. This is actually just this is a quantity that's approaching 1, and then the exponent is approaching infinity. So this is an indeterminate form. So that's an indeterminate form. Okay, so that means we need to use some other ways to evaluate the limit rather than using the direct substitution. Okay, so how do we start the problem? First, because in the base we have a variable, and then in the exponent we also have a variable. So it'll be easier to rewrite this expression into a form that it's easier for us to deal with. So the way to do it is that we are going to first let y be equal to this function. So we start by writing y is equal to x to the 1 over x minus 1. Okay, and then we take the natural log on both sides of the equation. Then we are going to get what ln of y is equal to ln of x raised to the x minus 1. Okay, so on the right hand side of this equation, we can see that there is exponent that we can bring to the front, because there is a log property that will allow us to bring an exponent of the argument of the log function to the front of this natural log. So we are getting ln of y, that's equal to 1 over x minus 1, and then times ln of x. So now that becomes a product. And then, of course, we can actually just rewrite this so that it will become a quotient. So we are going to get ln of y, it's equal to ln of x over x minus 1 here. So now what do we need to do next? We are going to start taking the limit now. So let's start taking the limit. So when we take the limit, we are going to just look at the limit this way. So we have limit as x approaching 1 from the right side of the ln of y. And that's equal to the limit as x approaching 1 from the right side of that right hand side, which is ln of x over x minus 1. And at this point, we actually don't need to worry too much about this side of the equation. We only need to compute the right hand side of the equation. So for the right hand side of the equation, if we directly plug the 1 in there, we can see that that's ln of 1. So the numerator is approaching 0. Okay, so the numerator is approaching 0. What about the denominator? As you can see here, 1 minus 1, it's also approaching 0. So we get an indeterminate form of 0 over 0. In this case, we can use L'Hopital's rule. So in the next step, we are going to differentiate the top and the bottom of the fraction. So let's try L'Hopital's rule. Then we are going to get what? We are going to get the derivative of the derivative of x is 1 over x. So we get 1 over x in the numerator. And then what about the denominator? The denominator would just be 1 when you differentiate the x minus 1. Okay, so if we are simplifying this, then we are getting this 1 over x. And then can we plug the 1 in now? Yes, we can, right? So the answer would just be equal to 1. Okay, so we actually have computed the limit of L1 of y, but we actually want the limit of y, right? So how do we find the limit of just y, which is this original function? What we are going to do is that we are going to just go back to our limit problem here. So we go back to our original limit problem, x to the 1 over x minus 1. And that's actually just equal to what? That's actually just equal to the y, right? Yeah, so that's just equal to the y. And then we can write this y as e to the ln of y. So you know that y can be written as e to the ln of y. You're really just putting the ln function into the exponential function, and so that composition of the two functions will actually just give you the y back. Okay, now we already know the limit for the ln of y is equal to 1, right? So we can just replace this ln of y, right? So in fact, this one right here is going to be replacing this ln of y. Okay, so our answer will just be e to the first power, which is this e. Okay, so the limit exists and is equal to e. And usually when you see this kind of limits where and for the function in the base there is the variable, in the exponent there is also the variable, and if we are running into a indeterminate form, then you can do it this way by just considering the function first and then take the natural log on both sides and then turn that exponent into in the front so that it will become a product. And then sometimes you can turn the product, that's an indeterminate product, so if we turn that indeterminate product into a quotient, and then we can apply L'Hopital's rule. So that's the big picture for this problem. Okay, so that's all for this problem. If you like this video, please subscribe to my channel and then give me some support. Thank you for watching. I will see you next time.